All right, 9-7 polygons. So polygons, again, they're different from circles, obviously. But next chapter, chapter 10, again, we're starting to enter our geometry realm. Chapter 10's all geometry stuff. Chapter 11's all geometry stuff. Polygons, one of the things here. So polygon, what exactly is a polygon here? It's a figure that has 3 or more sides. Okay. And we're going to go through it. But each side is a line segment. That matters a lot. Look at that in a moment. Each side is a line segment. And the line segments meet only at their endpoints. So polygons. So 3 or more sides to a figure. All the sides are line segments, straight lines. And the line segments meet at their endpoints here. So polygons get classified. You don't really say that's a polygon. That's a polygon. We say that's a square. That's a rectangle. That's a hexagon. That's an octagon type of deal here. So polygon is just a broad name of all the. Basically, we're separating them from circles. Circles are their own realm and their own terminology and everything. So it's either a square is a polygon, right? A square is a 4-sided polygon here. Officially, we call 4-sided figures quadrilaterals. We'll cover that concept later on in this chapter. 4-sided figures are unique because there's a number of 4-sided figures out there, such as diamonds, trapezoids, rectangles, squares, rhombuses. They're all 4 sides, but they're all different from each other in some ways. So that might be our next lesson, actually. Nope, 9/8 triangles, 9/9 congruent triangles, 9/10 compass, 9/11. That's our quadrilaterals. Yeah. 9/11. Okay, so and if you think about it here, I mean, polygon, it's enclosed here. So if I just draw that, I mean, that's not a polygon. There's polygons, we can find perimeter, area of them, all sorts of stuff there. That's not a polygon, that's an angle. All right, kind of looks like a triangle, but to truly be a polygon, it has to have minimum 3 sides. A triangle is the smallest of all polygons. And again, I can see I can just call it ABC, but this is indeed composed of 3 line segments, line segment AB, line segment BC, and line segment AC. When I connect them all together, I make a triangle. And again, 4-sided figures, 1, 2, 3, 4, 5-sided ones like that, and on it goes here. I mean, there's no real limits. Knowing the names of at least the first 10, we're going to rattle them all off here. So we'll go up to maybe 12. I don't know. 12 is fine. What do we have to do here? Go with this. Let me just see here. Some are easier. Some you already know. Some are really weird, to be honest with you. But we're just going to name them 3 through 10. And you should generally know the different classification, just how many sides they have. So polygons are classified by how many sides they have. Polygons, and then we're going to list them all off here. Are classified by how many sides they have. Okay, so let's go through them all. A 3-sided polygon. Well, we already know what a 3-sided polygon is called. It's called a Triangle. Right. Most people don't have issues with that one. I hope not. Number 4, again, we call them quadrilaterals. And again, you can look at 911 up there. Quadrilaterals get classified further. They're the only polygon that has further classifications. Triangles sometimes do. We're going to classify them by their angles and sides. But
10, right?
right. Okay. But we're classifying by angles and sides, not necessarily the type of polygon it is. So triangles have some special words. Four-sided figures, definitely. Future lessons, we cover both of these in depth. So, but the other ones here, continuing on, 5-sided figure, we call that a pentagon.
I knew it. Yes.
And again, when you think pentagon, you usually think of the building in Washington, D.C., and that's fine. We'll talk about perfect polygons. But the truth is, any 5-sided figure, like if I drew this right here, I could go 1, 2, 3, 4, and 5. That's a polygon, or that's a pentagon right there.
That looks like a square
1,
here.
2, this 1, 3, 4, really small angle right there, but 5-sided figure. Any 5-sided figure is called a pentagon. This probably doesn't look like a pentagon you would be thinking, just like an octagon, like a stop sign.
Can you do it where it's like this? So it's like.
As long as it's...
Do.
Yep, that's a pentagon.
Cool. That is the
correct.
beat. I didn't even realize. That's not the angle I drew it
No,
at.
that 1, 2, 3, 4, 5, composed of all those line segments that come together. To be a polygon again, I mean this 2, 3, 4, 5. Well, that's not a polygon at all. Polygon has to have all. There can't be this open gap here. If you have that open gap, it's nothing. It's just lines on paper. There's no classification of what that is. I'm just saying, a polygon, all the sides have to be fully enclosed here. Okay, that's what the line segments meet only at their endpoints. This one does not meet at the endpoint of another. So this is not a polygon at all. It has to be fully enclosed. All right, like this, like that, this, and this. That, not so much. And just when I drew that angle there, that's not a polygon. I have to connect all the sides together to be a polygon. So a 6-sided one we call a hexagon. Right. Hexagon, 6-sided figure. 7, again, this is called a heptagon. Not a common shape whatsoever. 8 is the octagon, like a stop sign. Stop signs are octagons there. Number 9, again, very rare, a nonagon. And then 10 is a decagon. So,
Can you draw a decagon for me?
not necessary, but 10 sides here.
Can you draw a heptagon for me?
We have other things to accomplish here today.
Wait,
So,
make number 9 is a nonagon?
nonagon, N-O-N-A-G-O-N.
Looks like a wall.
You can continue to classify. I mean, they all actually have names. They keep this going here. I mean, 11 side is a hendecagon. 12 is dodecagon.
Dodecahedron.
A dodecahedron is a 12-sided, 3-dimensional. 12-sided cube is called a dodecahedron.
I know one.
So hedron deals with 3-dimensional, like a dice, like a cube. So anyway, a different thing. We'll cover 3-sided, 3-dimensional figures later this year, but I mean, this is good here. But once we get up to a certain level here, they can call things an n-gon.
What is that?
Like, say, if I was dealing with like a 55-sided figure, and who knows the name of a 55-sided figure? Well, not me. There is a real name for it there, but I don't know what it is. So instead of calling it whatever it happens to be, we could call it a 55-gon, or any amount of sides. If there was 109 sides, we wouldn't try and figure out what the name of that is. So on and so forth here. So I would just call it a 109-gon, which again sounds a little weird, but it's just people don't know that. how far would you have to memorize this? But using this n-gon phrase here, you could literally just have any amount of sides and just say it's a 1078 gon or something here, so.
Do you do an infinity gon?
I don't know,
Like
again, it
it's
has to be
going
enclosed, so it wouldn't be a real thing. It would be impossible.
Maybe a circle.
Not so much. So the n-gon there, and they show, at least here in the hardcover book, they talk about find the sum of the angles of an 11 gon, a 15 gon, so on and so
What?
forth here. We'll
15 gon.
cover that here. And maybe on the back side, do they have anything like that? They do not, but we can look at them anyway there. Okay, so in the polygons, we're almost done here with vocab. Two real types of angles are going on here. I'm just going to draw a triangle.
Wait, can we put our notes?
Nope, two more terms here, and then we can flip over. So, interior angles. And again, we covered the concept of interior, exterior angles, but those were just kind of lines. There was no polygons formed by any of the angles we did before, right? I mean, the transversal and the alternate, those weren't shapes. Those were just some lines that intersected each other. There were no polygons there. So now, again, we covered interior, exterior angles, but for a polygon here, all right? And interior angles lie inside the polygon. All right. So if I look at my thing here, my interior angles are here. I'll just assume it's equilateral, they're all the same, but there are 3 interior angles to a triangle. However many sides it has is how many angles it has. So if I go back to the pentagon that I drew up here, it's got 1, 2, 3, 4, 5 angles inside of it. 5 sides, 5 angles. So same amount of sides in a polygon is the same number of interior angles it has. Okay? The interior angles lie inside the polygon. Exterior angles, right, lie outside the polygon. And but one more piece of information about these here that we need to know. I'll show you in just a second here. But exterior angles, how do I want to put this? Exterior angles are adjacent and supplementary to an interior angle. This is
So these are like reflex
big.
angles.
No, not reflex angles. Those are angles that are between
yeah.
180 and 360 degrees. So where are my exterior angles here? Well, if I keep these lines going here, as such, if I just kind of extend it out a little farther here, we see all these new angles are showing up. These are exterior angles. Exterior, 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 exterior. But if I would say the measure of this is 60 degrees here, the interior angle of this triangle, I know that interior and exterior angles are adjacent, which means they share a common side with each other. The old touch each other thing.
Yay!
But in addition to that, they are supplementary, which means they form a 180-degree angle, which means the exterior angle measurement of this triangle here is 120 degrees. This angle right here. And again, you can use properties about vertical angles as well to kind of make more, kind of spider this out here, so to say. But there is a direct relationship between interior and exterior angles. And if we know one or the other, then we're able to find more pieces of information about missing angle measurements here. Okay. I'm going to tell you now that we're not going to, looking at, we can start shifting over here, but I'm not really that interested in some of, I guess I'll go through it here, but they talk about the concept of concave and convex polygons. That's something we'll just cover next year. it's not, we'll go through the homework there, but it's not something I'm gonna ask you on a quiz or test, concave or convex.
So can we go?
And this concept with diagonals, I'm gonna show it to you here briefly, but it's not something I'm gonna quiz or test you on either, so it's not a priority for us, those concepts this year. Next year, we're gonna integrate that into the mix, but this year, not so much. Okay, good with vocab?
Yeah.
Great, all right. So let's go over to our notes here. I don't really ask you any questions about this on a quiz or test, however, it's not bad info to know. Through your homework there, assuming you completed the chart with the 10 things, just kind of match up the prefix to whatever, it shouldn't be real difficult. Like number 3, it says octa. How many sides do you think that means? Right, 8. So again, just should be pretty easy here, I think, right? Okay. Over here, again, you can kind of see we talked about, so number 9, what am I missing here? It's got 3 sides, it's got 3 angles, it must be a triangle. Number 11, 5 sides, how many angles?
Pentagon.
5, how many angles?
5.
5 angles, yeah, pentagon. So, you know, just complete the table. Once again, the chart that we made at the beginning will serve you well to help you just fill in the missing boxes here.
Actually, it wouldn't be square, it'd be quadrilateral.
Okay, guys, shh. So, next part here, find the missing measurements. So, what's the total degree measurement of any triangle?
180.
180 degrees. And we're going to introduce a new formula here in a minute to find some different things here. You'll need your calculator for that part, so if you don't have your calculator, you'll have one. Good. So now, if I can draw out a few things, but looking at number 19 here, it basically gives me something like this. And again, really helps to know that a triangle has 180 degrees. And what it's telling me here is this angle is 124 degrees, but I don't know what the other 2 angles are. Do I have enough information to figure out what they are?
Yes.
What do I know about the 2 missing angles?
They're equal.
They're the same angle. So how could I go about figuring out what how would you do it?
180 minus 124, and then you divide that number that you get by 2.
Right.
Boom!
So we know the sum of all 3 of these is 180 degrees. So I can subtract off what I know, 124, which means there's still 56 degrees unaccounted for somewhere in there.
28.
But I know that these are the exact same measurement. So this is the same and this is the same. And when I add those 2 numbers that are same together plus the 124, I should get 180. So since they are the same, you are right. Take what I know, there's 56 left. The 2 angles got to be the same measure, which means each one of them is 28 degrees. So if I said, give me the missing angle measurements, you could write the 124, but I need you to write 28 and 28. Do not write 56, because 124 and 56, that's only 2 angles. There's 3 angles here. Triangles always have 3 angles. So 56 is a key number. I don't dispute that, but that is not the measure of any of the angles. The missing angle measurements are both 28 degrees in this case here. What if I had something like this? I'll just say, so if I said, give me the 3 angle measurements for this triangle, or we can speed it up here. What am I missing there? What's that angle measurement?
40.
How do you know?
Yeah.
Because the square is the 90.
Right. We know that this symbol signifies a right angle. We've seen it before with the perpendicular line thing and all that. But right angles, go back to what we know about them, have a measurement of exactly 90 degrees. We covered that earlier this chapter here. So now I know what this is here. I see this, I go, oh, 90 degrees. And they're not congruent, but I know that's 50. So again, add up what I know. The 90 and 50 is 140. 180 minus 140, there it is right there. Missing a 40-degree angle here, so not too hard. What if I had this right here? What
They're
am I-
all 60.
60.
Right. And you'll learn this is called an equilateral triangle here, where all sides at angles are congruent to
What's
each
the
other.
isosceles triangle?
Isosceles, 2 of the 3 sides are,
Okay.
and then scalene is none of them. Yeah, we'll cover that later on this chapter,
Scalene?
but, right, so if I had this is what I would want you to write 60 degrees 3 times, because again, 3 angles, what are my missing 3 angles? Easy enough? Great,
Yeah.
all right, backside. So I don't care about this diagonal from vertexes right now, not something that's of value to us at the moment here. What I do care about though is finding the sum of the interior angles for each polygon here. So we're going to get introduced to a new formula. Okay,
8
So-
squared.
I'll call it formula to find
Fine.
the sum. And again, in the next part here, we're going to find the measurement of a single angle tube. So we're going to do 2 different things coming up here. But to find the measurement of a single angle, you have to know the sum too. So we're going to need this number here in a minute for 2 things. But the formula to find the sum of the interior angles of a polygon. Of a polygon. And here's your formula right here. It is in brackets n minus 2, and then times 180 degrees. And n equals the number of sides of the polygon
Times 180 or divided by 180?
times 180.
Okay.
Number of sides of the polygon.
So if it was a triangle, it would just automatically be 100.
Right, I'll show you how it'll all work here in just a second. And again, I mean, triangle, we already know the answer, but I can just use it. But however many it is, if it's a 3-sided, 7-sided, 15-sided, 74-sided, it really doesn't matter here.
Oh.
And when I say the sum of all the angles, I'm saying just like the triangle. The triangle has 3 angles. The sum of all the angles is 180 degrees. And let's use the triangle.
On your
So,
right, roll the 7.
how many sides does a triangle have?
3.
So, triangle.
Yeah.
6.
So therefore, if a triangle has 3 sides, I would say n equals 3, because n is the number of sides. So now I'm just going to plug that into my little equation here. And I go 3 minus 2. Always do your brackets first, and then multiply by 180.
Just 180.
Right, as you would expect it to be, because that's, But 3 minus 2 is 1. 1 times 180 means the triangle is 180 degrees. A rectangle, what's the degree measurement of a 4-sided figure?
360?
360, right. Think like a square, a 90, a 90, a 90, and a 90. 4 90-degree angles, 4 times 90, 360. But 4-sided figure, quadrilateral, if I test it out here, this time n would equal 4. 4-sided figure, so plug it in. 4 minus 2 times 180. 4 minus 2 is 2 times 180 degrees, 360 degrees, right?
So if you get it can go up any amount of numbers.
Right.
You don't have to go
That's
down to
where
180.
that's where the n god comes into play. Like if it's just, you tell me, if I had a 15-sided figure, what's the sum of all 15 of those angles?
13 times 180.
Right,
whatever
is, what is it? Punch it in. So a 15-sided figure, plug it in this case,
2,340.
and that's the sum degree measurement of all 15 of those angles.
Oh, I get it.
If I add up all 15 of those angles, it should be 2,340 degrees,
Okay.
right?
Yeah.
And that's all you do. It just, however many sides. So I'll just sketch one roughly out here. You see some different looking things here. So I'll just put one out here. But what you're going to want to do is probably figure out how many sides are on this guy. I'll make some points here to hopefully make it a little easier. But my question to you is, what is the sum of all these interior angles of that figure?
Yeah, it's 900 degrees.
Yeah, it's 900.
Is it?
Yeah, it is.
How many sides do I got?
7.
1, 2, 3, 4, 5, 6, 7, right? N
Seven.
equals 7. 7 minus 2 times 180. 5 times 180. That sum of all of them, 900 degrees. Easy enough?
Yeah.
Okay, next part. Find the sum of the, so same thing, find the sum, but then take it a step further. Find the measure of a single angle.
That's
Now,
not bad.
just for a moment here,
Oh, and
we're
you
going to
divide it by
cover,
how many sides it is?
huh?
You divide it by how many sides it is?
Correct. I'll show,
Okay.
I'll show you in a minute. But a concept, a term here, I'll write it down here. You don't have to go back to your vocab here. But they call it a perfect polygon. And all sides and angles are congruent. So when we're figuring out the measure of a single angle, it has to be a perfect polygon, a perfect hexagon, a perfect octagon. Because if it's just one of these, like what, this right here, well, clearly this angle and this angle and this angle are not all the same measure, right? And they're not perfect because they're not all the same measurements. Again, that's why. This is much longer than this. That's why it's not a perfect polygon. So when we're doing any of these, again, it's not, there's no curveballs here. It's not, oh, sorry, it wasn't. Actually, you can't do it. They're all considered perfectly perfect. And they look real nice and perfect, right? Everything's the same and all that here. So to find, we'll just look at 27. How many sides does that thing have?
A lot.
27 has
1, 2, 3, 4, 5, 6, 7, 8, 9.
10.
I got 9. Did I count right?
1, 2, 3, 4,
That's
5, 6, 7, 8, 9. I got 9.
Yeah.
9?
Bronze.
Okay.
Yay.
So here's our formula to find the interior angle thing. Formula to find measure of a single angle. Okay, you ready for it? So n minus 2 times 180 degrees, which at this point here is the exact same formula we just had. The only difference now is we're going to divide by n, where n is still the number of sides here. So I'll go back to the triangle for a second here. And we know n was 3, right? So 3 minus 2 times 180 divided by 3. 3 times 2 is 1, times 180 is 180, divided by 3. The sum of a perfect triangle, or an equilateral we call it, but a perfect triangle would be, again, all three of those angles would be 60 degrees. We know the square final answer should be 90 degrees, 90, 90, 90, 90. But plug it in. 4 minus 2 is 2 times 180. Divide by 4. 2 times 180 is 360. Divided by 4. The sum, or the measure of a single interior angle is 90 degrees. All four of them are the same measurement. So for 27, what is the, we already agreed it's a 9-sided figure. So what's the measurement of those interior angles?
1,260.
A single angle.
Oh, a single angle.
Right. The sum of all the angles is 1,260. That's the sum of the total measurement. But a single angle is 140 degrees. Take your 1,260, divide by 1, 2, 3, 5, 6, 7, 8, 9. That's telling me 140, 140, 140, 140, 140, 140, 140, 140, 140. They're all 140 degree angles, all of them. and they add up to 1,260 degrees. Easy enough?
Yeah.
All right, last part here. Now we introduce some of these exterior angles where we need to use some of our knowledge here to kind of fill them in. So we'll do 31 and 33 here. So for 31, what they want to know is what this angle measurement is right here. D. You don't have to sketch it out here. We can probably talk this through a little bit here. And we'll talk through 30, 32, and 34 tomorrow. We'll hash it out. But what do you think D is?
Oh, the exterior.
How do you, right there, that's what I want to know. I want to know the measure. It is an exterior angle.
I thought I was talking about that.
It's 30.
No.
No, it's not 30. It's 150. 150.
50. Right, and it goes back to what we know to be true here on back in our notes here. Exterior angles are adjacent and, this is the big thing, supplementary. What are
So-
supplementary angles?
Equals 180.
Two angles that measure up to 180 degrees. So to solve for D, first we need to understand our congruent arcs, right? Because there's my arcs, that's telling me this is 30 degrees because of the arc. And then I know the measurement of the interior plus the exterior will always total 180. So 180 minus the 30 is 150. What about E here? That's an interior angle. What's the measurement of angle E?
Number E.
On number 33. There it
Does
is.
that equal 360 or? Oh wait, never mind. I know how
1,
to
2,
do
3,
it.
4, 5 sides.
Right, so
I
you
have
probably
it.
want to know the total degree measurement.
Wait, hold on. I'm
That's a
gonna cut.
key number you're going to need. You're going to want to know what the total measurement of all the angles is. And then start using what you know to be true to kind of whittle your way down there.
I don't think I'm doing that right, but alright. It's good enough.
There's a couple different ways you can get here, but the key is you need to know how many sides is that figure? 5. What's the total degree measurement of a 5-sided figure?
But oh,
540.
540, right. So I know the sum of all 5 of those angles is 540 degrees. How many angles do I know the measurements of? 4 of them. So there you go.
oh,
So start subtracting from 540.
360.
72.
72 is correct.
Yay.
Oh, I forgot to. Never mind. Yeah.
90 plus 90. Oh, that's
So however you want to do it, but you need to do 540. And again, you can use your n minus 2 to get there. That would give you 3 times 180. There's your 540. So that's how you can figure out. So now I go, okay, this, and this, 540. But I know these two are 90. So subtract 90, subtract 90. That's 144. Subtract that. That's also 144. There's the congruent arc. So 540 minus 90 minus 90 minus 144 minus 144. All I'm left with then, 72 degrees. That's what this one has to be. Has to be 72 degrees. Okay. So again, these are good. They challenge you a little bit, see what you know about what you remember about things. But to figure out, especially for these here, you're going to need to know the total angle, some of the interior angle measurements.
Alright, we
'cause-
got.
Almost, but yeah, I mean, you'll want to know what these are here, so you know where you're working backwards from. This one here, again, you'll calculate a single interior angle, but then understand that's not what I want. I want the exterior there. This one's interior too, so. We will check it tomorrow. Do get the homework. We'll throw it on the rubric, most likely, so. And you owe me 2 for tomorrow too.
I have
right?
one of them done and the other one is almost done.
Tomorrow. Are we staying in for recess?